Good morning, my name's Nick Tudor. I'm one of the founders and directors of a company called D-RisQ Limited that's based at Malvern Hill Science Park here in Malvern. And what we do is assure software, and that means basically software that if it goes wrong, then there's a potential for somebody to get injured or even be killed as a result of it. So we're talking about aircraft software, cars potentially, autonomous systems, that sort of thing. And what we're basically employing here is the ability to use some mathematical techniques to prove that software does what you want it to do, but more importantly to prove that it doesn't do what you don't want it to do ever, and then to show what happens when, not if, something goes wrong. And these techniques are built on some maths that came out of the early 20th century, around 1900s, some Polish and German mathematicians, and then it was built upon by the likes of Alan Turing and Tommy Flowers during World War II, and to build the Colossus computer and to break Lorentz code. And then it came a discipline in about the 1960s from a Dutch mathematician called Edgar Dijkstra. And the four methods, as it's called, as the discipline is called in software engineering and computer science, is the foundations behind all computing. So at the end of the day, you've got to realise that, of course, that a computer only talks in binary. It's either a 1 or a 0, it's either on or off. So if that basically it means it's a big number. And if it's a big number, then I can do some maths with it. I can do some what's called proof. As opposed to doing a whole load of tests, which may not check that all the right ones and noughts are in the right order, just check some of them some of the time. So it's a much stronger set of evidence you can get from the use of this process than you may be able to get from tests, and particularly where you're trying to show the absence of behaviour through the never behaviours. So why are we doing the things that we do? Well, the maths behind it, of course, is very difficult. Otherwise, everybody would have done this some time ago. That's the first reason. The second reason is you need an awful lot of computing power to be able to do this kind of technique, and obviously a lot of memory as well to go with that. So what we've been focusing on is automating these processes as far as we possibly can, and provide the evidence that can support, for example, aircraft certification, or show that an autonomous system is in fact safe. So what we've been focusing on now that we've got the maths and we've done an awful lot of research in the mathematics ourselves, and obviously in the automation, bringing up that now vast resources we've got in terms of processing power and memory, and we can automate these things. And that means that the power of these mathematics is very much available to a typical engineer you might find in an automotive company or an aerospace company or medical devices or wherever it happens to be. And they don't actually have to learn how to use four methods. So the tagline we have is, if you know how to use a laptop, but you don't need to know how the laptop works in order to be able to use it. And that's the same approach that we're using with this. So does it work? Well, a couple of years ago, we did a series of trials, of blind trials, with an automotive company, and the product has now actually reached the marketplace. And we showed for a safety critical system, that a battery charging system on the car, that it will always do what you want it to do, and obviously again it won't do the things like overcharge and explode, or that it enables the car driver to drive away whilst the charge lead is still attached. Then people don't get a bit upset when they rip the side of their car out or rip the infrastructure out of the ground. So we showed that we could use this technique as an embryonic kind of a technique, and we gave the trial to other people to use, and they seeded, in this example, some 48 errors into the process. And in particular, this is at the requirements phase down to the design phase. And we showed that against their benchmarks, we were able to make around 80% savings, even though our tools weren't yet productionized for standard users. And we also showed that not only could we find those 48 errors, but actually we found all 49, because who'd have thought in a software engineering project that somebody got something wrong and didn't know about it. That's pretty standard. And in fact, more recently, with the more productionized tools, we've allowed an American company to use them on some software that they've actually already developed, gone through flight trial, and they'd found an issue all the way through. All their verification processes and validation processes were complete. And as I say, they were in the air and they found an issue with some software. Fortunately, this wasn't safety critical. They used one of our tools on that, and they found found the error that they were looking for, but they also found that they had a second error as well. So this is the kind of power that we have with this, to be able to save an awful lot of money and therefore cost that goes with that. So we've also used the tools to do some things with autonomous systems, which I talked about earlier. We've put a decision-making system onto an autonomous boat, and we showed that it would always comply with the rules of the sea. That's the way in which everybody else would expect it to behave, just like the rules of the road, perhaps. What we did was we put a piece of software on there that took the inputs from all the sensors, we codified the rules of the sea, and then we allowed the boat to go and do what it needed to do up to the point where it became unsafe, and then our system kicked in and took over control. And then moving forward about a year or so, we ended up doing the similar sort of thing for an autonomous aircraft and showed that it would always comply with the rules of the air. In fact, we took that a little bit further and we showed that it would actually behave the way a pilot would behave. So when things got really messy, the rules would be a bit staid, and it wouldn't necessarily be a good idea to be in strict adherence with the rules. So we showed it would do a slightly different behaviour, and that was fully autonomous. And in both these cases, in the boat case, we took it to sea and showed it would do that, and in the air, we flew two aircraft at each other, and ours got out of the way of the other aircraft, and we had that videoed in the air as well. So where are we going with this? Well, not only do we tackle the autonomous systems in air and sea, we're also doing an underwater program with nuclear decommissioning and offshore inspection and intervention. And we're also applying these techniques in the cybersecurity world as well. So cybersecurity is obviously a very high-profile issue with everybody these days. What we've got is the ability to be able to detect distributed attacks across a network in real time, which is something we believe that not many people can do, if anybody at all. And the way to think about this is, if you have your network and you think of that as a field full of haystacks, some nefarious individual has hidden a needle in amongst those haystacks. Those haystacks represent the nodes on your network, and what he's done before he actually hid this needle in the network is he painted it to look like straw and then broke it up and scattered it through some of the haystacks. And what we're doing is the ability to identify every single strand of that needle in real time and saying you're under a cyber attack of a particular type. And by doing that, we think we can assist in the fight against cybercrime in various ways. So the industries that we're looking for, and I mean we are hopefully now working in, is obviously aerospace and autonomous systems, probably in the finance sectors as well. And hopefully saving people an awful lot of time, an awful lot of money, and therefore getting products to market faster than they would otherwise have been able to do.